Welcome to this explainer. Today we are diving straight into a core topic of the Cambridge Igcse Computer Science syllabus, specifically Chapter 10, and we are going to completely demystify a concept that is absolutely fundamental to your programming success: arrays. Whether you are studying for syllabus 0478, 0984, 2210, or even building foundations for A-Level 9618, understanding how to structure data is non-negotiable. If you've ever found yourself writing out code and feeling completely overwhelmed by trying to keep track of dozens or hundreds of individual variables, well, you are not alone. It's a common roadblock. But today, we're going to clear that roadblock entirely. This is the exact strategy and knowledge you need to turn chaotic code into streamlined, examiner-pleasing logic. Okay, let's dive right into this and get your exam game plan sorted.
Here is our roadmap for this session. We are building step by step. We'll start with number 1, the variable overload problem. Then move to 2, one-dimensional arrays. 3, iteration and loops. 4, the linear search. 5, managing grouped data. And finally, number 6, the ultimate data structure for your exams: two-dimensional arrays.
Let's kick things off with Section 1, the variable overload problem. To really appreciate why arrays were invented in the first place, we first have to understand the specific problem they were designed to address. Because in computer science, every tool exists to solve a very specific headache. Imagine you are a teacher, and you need to write a program that records a simple to-do list, or maybe you need a system that tracks the names of 25 individual students in a single class.
Think about how you would code that without arrays. Storing 25 student names as individual, standalone variables, student 1, student 2, student 3, all the way down to student 25, is an absolute nightmare for any programmer. It is highly inefficient, it makes your code incredibly long, and it's a massive pain to manage or update. If a new student joins, you have to rewrite your actual program to add student 26. But arrays, they provide the elegant, professional programmer's equivalent of a single, manageable list. Instead of creating 25 separate, scattered boxes in your computer's memory, you get one neatly organized filing cabinet under one single name. It's a total game changer for your code's efficiency. Before we continue, subscribe to our YouTube channel Ace the Exams at Ace Exams IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on to Section 2, one-dimensional arrays. So what exactly is this filing cabinet? What is an array fundamentally? And how do we build our very first one in our code?
Let's lock down the formal definition, because you need this clarity for your exam answers. An array is simply a data structure holding multiple items of the exact same data type, all grouped under one single name, which we call an identifier, rather than just holding one single value like a standard variable does. The crucial part of that definition is the same data type. If you declare an array of strings, it only holds strings. If you set up an integer array, it strictly holds integers. You cannot mix and match text and numbers in a standard one-dimensional array. It's a uniform collection.
Now, what's really interesting, and where a lot of students lose marks if they aren't paying attention, is how we actually find the specific data once it's stored inside that array. Let's use the first 5 letters of the Greek alphabet as an example here. Each data item is identified by a unique sequential number. We call this the index. And crucially, in many programming environments, this index starts at 0, not 1. This is known as zero-based indexing, and it's exactly how languages like Visual Basic handle arrays by default. So the data item alpha lives at index 0. Beta is at index 1. Gamma is at index 2, and so on. It feels a bit unnatural at first because humans count from 1, but computers, they start counting from 0.
When we declare arrays, meaning when we tell the computer to create them, the rules actually change slightly depending on whether we are writing Cambridge pseudocode or actual high-level code like Visual Basic. This is a vital distinction for your Paper 2 exams. Pseudocode requires you to be very explicit. You have to state both the lower bound and the upper bound. You literally write array 0 to 4 of string. But in Visual Basic, the language automatically assumes that the very first index is always 0. So when you write the declaration, dim Greek letter 4 as string, you are actually asking for 5 memory spaces, index 0, 1, 2, 3, and 4. You have to keep this distinction sharp in your mind depending on whether you are answering a pseudocode question or writing program code.
And this brings us directly to a golden rule pulled straight from the source material. Quote, "It is crucial that you remain consistent when declaring and using an array." Why does this matter so much? Well, let's say you set up an array using zero-based indexing, but later in your code, you write a loop that starts counting at 1 to read that data. That is a very common pitfall. If you do that, your program will completely skip the very first item at index 0. Even worse, it will likely try to read past the end of the array at the very end of the loop, which will completely crash your program. The examiner is looking for this. Consistency in your logic is absolutely everything. That perfectly sets up Section 3, Iteration and Loops. Now that we have a one-dimensional array correctly declared and set up in memory, how do we efficiently read from it or write to it? We definitely don't want to go back to manually typing out every single index location one by one. That defeats the whole purpose of using arrays in the first place.
This is where the real coding magic happens. We can supercharge our arrays by pairing them with loops, specifically a for loop. Because our array uses a perfectly sequential index, 0, 1, 2, 3, 4, we can use the loop's counter variable to act as our index pointer. It automatically iterates through every single position. You just set a for loop to run from 0 to the maximum index of your array, and inside the loop, you use the loop counter to target the array. Boom. With just 3 lines of code, you can sequentially read, write, or process thousands of data points without breaking a sweat. It's incredibly powerful.
All right, moving into Section 4, the linear search. This concept of using a loop to iterate through an array leads us directly into one of the most important algorithms you need to know. If we can loop through an array from start to finish, we can also search through it to find a specific piece of data. This foundational algorithm is known as the linear search.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Now, look at the logic required for a linear search. It's brilliantly simple but highly effective. We start our search at the very first index of the array, index 0. We look at the item inside. We ask the computer, is this the specific data we are looking for? If yes, fantastic. We trigger a match found routine and stop searching. But if it's false, the counter increments by exactly 1 and we check the next location. We check sequentially, one by one, right down the line.
So, to break the algorithm down into a simple, step-by-step mission, Step 1. Start at the first array index, usually 0. Step 2. Check if the current data matches your search criteria. Step 3. If it's not a match, increment your loop counter to move to the next index. And Step 4, you stop the search either when you successfully find the data or you reach the absolute end of the array and output a message saying no match was found. It's a very thorough algorithm. However, as the source text wisely points out, if you are searching through an array containing 100,000 mobile phone numbers and the number you want happens to be the very last one, a linear search might take a little while because it has to check 99,999 wrong numbers first.
Let's progress to Section 5, Managing Grouped Data. So far in this explainer, we've only put single, isolated pieces of data into our arrays, like a single Greek letter or a single student's name. But in the real world, and in your complex exam scenarios, what happens when our records get more detailed? What if we need to store a student ID, their surname, and their final computing grade all together as one logical record? One traditional solution to this is using parallel one-dimensional arrays. Let's look at a system handling data for newborn babies. We can declare one array specifically for the baby ID, a completely separate array for their gender, another separate array for weight, and a fourth array for blood group. The clever trick here is that the exact same index number across all these different arrays links the data together. So whatever data is sitting at index 0 in the ID array belongs to the exact same baby as the data sitting at index 0 in the weight array and index 0 in the blood group array. The index is the glue that holds the record together across multiple lists.
While parallel arrays definitely work, and they keep things logically organized, managing 3, 4, or even 10 separate arrays can get really messy when you're writing code. If you want to move or swap records, you have to remember to swap the data in every single array at the same time. It prompts a very important question for any serious programmer. Isn't there a cleaner, more efficient way to store multiple data elements for a single record?
That brings us to Section 6, which holds the answer to that question. This is the final boss of our explainer today, and a key differentiator for top-tier exam grades, the two-dimensional array. Let's see how this massive upgrade completely transforms our code. Instead of juggling multiple parallel 1D arrays, a two-dimensional array holds everything under one single unified identifier. It does this by using a combination of two index sets instead of just one. The best way to think about it is as a grid, like a spreadsheet that contains multiple rows of data intersecting with multiple columns. Let's look at this student table to see it in action. If we want to access the student Rodriguez grade, which is an A, we don't need parallel arrays. We just look at row 0 and then move across to column 2. In your code, this specific element is identified simply by two numbers, index 0, 2. It is almost universally structured as row first, column second. You basically have an entire spreadsheet-like structure living effortlessly under one single variable name. It is incredibly clean.
Now, as humans, it's highly helpful for us to visualize these 2D arrays as a grid drawn on paper. But notice how you can actually flip the orientation? You can make the data span horizontally across rows or run vertically down columns. That orientation is actually an arbitrary choice made by you, the programmer, depending on how you want to design your loops.
And the reason it's an arbitrary choice is perfectly summarized by this brilliant quote directly from our source text. The array is not stored as a grid in your computer memory. Crucially, this grid is just a mental model. Your computer's RAM doesn't physically carve out a two-dimensional box on the silicon. It's simply a structural concept, a logical mapping, designed to help us, the human programmers, visualize the data and easily write loops to read and write grouped information.
So, let's wrap up everything we've uncovered today, because this is the core strategy you need to take into your exam. Arrays are powerful tools that transform chaotic variable overload into unified, manageable data structures. Remember the key takeaways. They are typically governed by zero-based indexing. They only unlock their true time-saving potential when powered by iterative for and while loops, and they scale seamlessly from simple one-dimensional lists all the way up to comprehensive two-dimensional data grids. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
We've mastered 1D and 2D array structures today, and if you can apply these confidently, you are well on your way to acing your computer science coding logic. But as we finish, I want to leave you with a fascinating thought experiment. If a 1D array is just a straight line of data, and a 2D array is a flat grid like a spreadsheet, what kind of complex real-world data would force a programmer to add a third dimension to their array? Think about 3D space, or perhaps tracking data over time. Ponder that as you continue your coding journey. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.